In this video, I'm going to go over practice exercise 17, parts A and B. So this is the practice exercise following up the lecture on polyprotic acids. So reading over the question, part A, it says calculate the pH of a 0.020 molar solution of oxalic acid, and you're given the two Ka values. So if this was on an exam, you might have to look at the cover of the exam to get the two Ka values, or they would be given to you within the problem. So right away, we'll start with part A, and then we'll start to talk about part B. So just looking at the problem, I know that oxalic acid is polyprotic, specifically it's diprotic, because there's two H's out front, so it has two acidic hydrogens, and I have a Ka1 value and a Ka2 value. So let's think about what is in a beaker of oxalic acid. So if I had a container, and in this container, we know we have 0.020 molar H2C2O4 aqueous. I know it's aqueous because I'm given a molarity of it, therefore it's dissolved in water. So if I had microscopic eyes, what would we actually see in that beaker? Well, I know I have some of the H2C2O4, the fully protonated acid. I also know I have some of the acid that lost one proton, so HC2O4 minus, as well as C2O4 2 minus. So the fully protonated acid, the acid that lost one proton with a 1 minus charge, and then the form that lost two protons with a 2 minus charge. Additionally, in that beaker, we would have H2O as well as hydronium, since this is an acidic solution. And I know my two acids, H2C2O4 and HC2O4 minus, I know that this is my stronger acid. Compared to this, because Ka1 is greater than Ka2. So the first thing we should do is write down our two Ka reactions for this acid. So I know my Ka1, I always start with a fully protonated acid, so H2C2O4 aqueous. I know my Ka reaction, I'm reacting with water. These are always hydrolysis reactions. I know their equilibrium. So again, my acid reacts with the base. Acid is a proton donor, so I form HC2O4 minus, aqueous. My base accepts the proton, so I make H3O plus, aqueous, so the conjugate base and the conjugate acid. And I'm given the numerical value Ka1, 5.9 times 10 to the negative 2. And now let's look at Ka2. I always start with the species I just formed. So I form H2C2O4 minus. That's the reactant always in my Ka2 reaction. So I start with C2O4 minus, aqueous plus water, liquid, and equilibrium with C2O4 2 minus, aqueous. So my oxalate ion plus hydronium. And I see that my Ka2 is given as 6.4 times 10 to the negative 5th. So I can see Ka1 is larger than Ka2, so H2C2O4 is a stronger weak acid than HC2O4 minus. So Remember, if I have a mixture of acids, I can get the pH of the solution that contains a mixture of acids by focusing on the stronger acid only. So what does that mean? That means if I have a polyprotic acid where Ka1 is significantly larger than Ka2, I can focus on my Ka1 reaction to find the pH. So what I need to do is I can find my hydronium at equilibrium from just this first reaction and then solve for my pH. Negative log of hydronium. So let's go ahead and do that. So go to this next slide. So again, to get the pH of a polyprotic acid, we can focus on Ka1 only, assuming Ka1 is significantly larger than Ka2. So how do we get the pH of a weak acid? Remember, the first thing we have to do is write down the reaction and the Ka expression. So we'll write that again together. I'm going to start with H2C2O4 aqueous. And a Ka reaction is always hydrolysis, because that's what's in your beaker. The acid reacts with the water to produce H2C2O4 minus plus hydronium. I know my Ka1 expression. Oops, let me erase. Should be H. I lost one proton. So hopefully you caught that mistake of mine. H, C2O4 minus, and my Ka1 expression is H, C2O4 minus times hydronium divided by H2C2O4. I do not include liquid water because liquids do not show up in my Ka expression. Step 2 is my standard icebox, ICEQ. I know I'm going to change signs underneath my equilibrium arrow. I do not include water because it's a liquid. It does not show up my Ka expression. And again, this is really a grid. So the icebox allows us to keep track of the concentrations of the reactants and products. You're told it's a 0.020 molarity solution. Nothing is mentioned for the product, so it's 0. Again, at equilibrium, what happens is I have a change. I'm going to use up my reactant, so it's minus X, and I make products plus X and plus X. It's a 1-to-1 mole ratio, because all of my coefficients are 1. And then for EQ, I add up the columns, so I end up with 0.020 molar minus X, X, and X. Now we're at step 3, stop and think. How do I solve for X? Well, I'm given a Ka value. So I know that my Ka, right, products, which is X, hydronium, which is also X, divided by my reactant, which is 0.020 minus X. So now to solve for X, I use Ka because I'm given that numerical value. So I have 5.9 times 10 to the negative second equals X times X, which is X squared, divided by 0.020 minus X. So 5.9 times 10 to the negative second, that is not a very small number. That's just 0.059. So we're going to have to use the quadratic formula. But let me show you how to see that X is not actually small. So let's say we did try and use the shortcut. is x small, so our 5% rule. So remember, I would make that equal to 0. 5.9 times 10 to the negative second equals x squared divided by 0.020. And now I can quickly solve for x. So x is the square root using algebra. 5.9 times 10 to the negative second times 0.020. So let's go ahead and type that into the calculator, see what we get. So 5.9 second e negative 2 times 0.02, enter. Second function radical, second function answer. And I got x is 0.034. And now we have to check, is x small compared to the number it was being subtracted from? So this is x, and this is the number it was being subtracted from, 0.02. So x is actually larger. To type in and calculate exactly what is that number, you would take x, which is 0.034, divided by the number it was being subtracted from, times 100. And so we see it's actually larger. And how much larger is that? We can see that x is 17% larger than 0.02. So that tells us the shortcut does not work. Okay, so since x is larger than the number we were subtracting it from, it obviously does not work. So what does this mean? That just means we have to go back and use the quadratic formula. So we know that our k value is 5.9 times 10 to the negative second, which equals x squared over 0.020 minus x. So now we go ahead and use the algebra that we know. So we have to multiply 0.020 minus x by both sides. And I'm going to distribute, so 0.059 times 0.020 on my calculator gives me 0.00118 minus 0.059x equals x squared, and rearrange to get into the form 0 equals ax squared plus bx plus c. We end up with x squared plus 0.059x minus 0.00118. So now I can see a equals 1, b equals 0.059, and c equals negative 0.0018. So now I'm going to go ahead and go on to a quadratic formula calculator on the computer and plug in for a, b, and c, and the two values of x that we get. One value is x equals 0.0158, and the other value of x is negative 0.0748. So now we have to figure out which value of x is correct. We do that by looking at our icebox. I see that x stands for my equilibrium molarity, therefore it cannot be a negative number. So our value of x must be 0.0158. And I can see that stands for my hydronium molarity at equilibrium. So lastly, we're asked to solve for the pH of this problem. So again, the first thing I did was realize I had to use the quadratic. The second thing I did was using the quadratic. And now the third thing I'm going to do is use my pH equals negative log of hydronium at equilibrium. I know that's just my x value, so pH equals negative log of x, which is my 0.0158. And so plugging that into the calculator, we get pH equals 1.80. And again, I have 2 sig figs in my molarity and my Ka value, which results in 2 digits past the decimal for my pH.